Okay, thank you, dear moderator, for giving me the floor. Greetings to all esteemed members of the conference. I'm Marie Kepdieu. I'm a Ph.D. student from the University of Yaounde I, Cameroon, Central Africa. I express my gratitude to the organizing staff for this opportunity given to me to participate at this conference. Please allow me to introduce my presentation. It is titled Equilibrium, Thermodynamics, and Kinetic Studies of Palm Oil Beta-Carotene Adsorption by composite-based Silica Smectite clay. In this work, we use two low-cost materials, a smectite clay and a rice husk, which are readily available to synthesize three silica smectite composites through very simple and eco-friendly methods. And the obtained products were used for palm oil bleaching. This work has been co-authored by Dr. Gustave Chana of the University of Yaounde I, Dr. Jacques Romain Dimou of the School of Chemical Engineering and Mineral Industry, University of Yaoundé. I would also like to thank Professor Chantan Jumunjangan of the University of Yaounde I, Sandra Andraga Mekanyanu from Madhya Department of Chemistry, Biochemistry, Physics and Engineering, Indiana City of Pennsylvania, and Professor Chetli Chizawi from the Department of Chemical Engineering, Swansea University in UK. This is the summary of my presentation. On the first point, you have the general information about beta-carotene. On second point, why are we using silica smectite composite for oil bleaching? And the third point, what are the aim and the objectives? Fourth point, methods. Fifth point, results and discussion and conclusion. With no doubt, palm oil is the most widely used vegetable oil in the world. It's covered more than 40% of the worldwide production. Its deep color is due to the presence of beta-carotene. And that color of beta-carotene is due to a conjugated double bond system in the molecule. Some previous work said that excessive consumption of beta-carotene may increase the risk of cancer and cardiovascular and liver diseases in smokers and alcoholics. And the presence of beta-carotene in palm oil is also aesthetically undesirable because it's sometimes very challenging to control the final color of palm oil-based product. In food industry, for example, palm oil is used in the production of various foodstuffs, while in cosmetic, it is served to the production of some basic oleochemicals. In addition, palm oil is also gaining a significant interest as one of the preeminent renewable sources for the biofuels industry. Therefore, the removal of beta-carotene from palm oil is crucial for all the aforementioned applications. In the palm oil refining process, either in the chemical or physical refining process, the decolorization, that means the removal of the color compound, is one of the crucial steps. and the removal of that beta carotene, who is the main responsible of the colors, is done by performed or is achieved through absorption on adsorbents such as zeolite, silica, activated alumina, smectite clay, and so on. And clays are generally activated with mineral acids and bases, as well as thermal treatment in order to enhance the bleaching yield. However, this efficiency improvement process is not without its disadvantages in terms of the toxicity of some chemicals used, the durability or the reusability of the absorbents. You know, the sustainability requirements of an interesting absorbent, like any other materials, should encompass its efficiency, eco-friendliness, cost effectivity, design flexibility, and recyclability. To meet these requests, composites are most advisable due to their synergetic and heterogeneous properties gained from their basic constitutive components. Moreover, composites based on natural resources have been widely proved in the literature to be of great interest and advantageous based on the physical-chemical characteristic of the products. And smectite clays to know a growing interest in composite synthesis due to their their structure, which provide the accessibility into the interlayer species, giving the possibility of inserting some molecules with chosen properties. We also know that silica has some advantages, has low toxicity, high reactivity, and also give the possibility for functionalization. And some previous work has the one of Solin and collaborators in a paper published in 2008 and 14, titled Natural Mixture of Silica and Smectite as a New Clay Material for Industrial Application. They came up with this, the potential uses of silica smectite mixture. But such natural deposits are generally limited to meet the height demand. Hence, they need to synthesize such mixture. And the literature shows several possible combinations of silica and smectite. The silica can be distributed on the surface of the phyllosilicate matrix. The silica can be intercalated in the interlayer species. They can be dispersed in the phyllosilicate matrix or form core shell particles. That's what we found in the literature. And we noticed that all the silica precursors used in those work are generally synthetic precursors like TMOS, TEOS, silicium tetrachloride, and other chemical products. In the developing countries as Cameroon, it is important. And those methods, first of all, are using chemicals. Synthetic precursors generally are less eco-friendly and sometimes more complex and expensive. And in developing countries like Cameroon, it is important to work regarding to the sustainable development. And we think that, and it's also proof in the literature, that there are some low-cost materials, like pharmacies like sugarcane bagasse, corn cob, rice husk, and many others that are quite rich in silica and could be then explored in such synthesis of silica smectite composite. So we think that replacing the synthetic silica precursor with a natural precursor will made it possible to and easy to synthesize silica smectite composite and further minimize the use of chemicals that are sometimes expensive. And despite numerous studies on experimental parameters affecting the adsorption process, the assessment of the adsorption efficiency of silica smectite clay-based composite remain unexplored for bleaching purpose. And that's what we are proposing in this work. And in the same line, the investigation of the kinetics, the equilibrium, the thermodynamics of the beta carotene adsorption on such combined materials on such combined materials will be studied. Okay, concerning our methods, the three synthetic pathways differ from each other by the form of the silica that is combined to the smectite clay. In fact, a silica sludge have been prepared. A silica sludge have been prepared from acid treatment of rice husk hash, and the sodium silicate have been obtained by alkaline dissolution of the silica sludge. And in the third pathway, we prepare nanosilica powder by hydroxylation polymerization of the sodium silicate solution. All of them came from the rice husk ash. So for the synthetic pathway, the silica, the local smectite clay was respectively mixed for the pathway 1 with the silica sludge, the pathway 2 with the sodium silicate, pathway 3 to the nanosilica, and it was maintained in searing to obtain gels. After oven drying, we obtained 3 powders, labeled CSS1, CSS2, and CSS3. That were the different powders were analyzed by X-ray diffraction, by infrared spectroscopy, scanning electron microscopy, coupled with energy dissipative X-ray, and BET specific surface area measurements. Concerning the bleaching process, the bleaching process was conducted through bath tests, and the measurements of the concentration of beta carotene remain in oil were performed by visible spectrophotometry. As I just said, the work are still ongoing. I will present some of the results that have been obtained. And concerning the RD patterns, it is evidence that the 3 composites, CSS1, CSS2, and CSS3, have increased amorphous phases due to the added silica. We can also notice there the presence of some peaks related to smectite and kaolinites as clay minerals associated to some minus non-clay minerals. Concerning scanning electron microscopy, all techniques show an heterogeneous morphology where the distribution of silica particle in the clay matrix change with each synthetic pathway. For the silica through synthetic pathway, a predominantly three-dimensional like structure with a ferrosilicate matrix skeleton was obtained. And for the pathway using a silicate solution, an amorphous compound with limited intergranular cohesion containing silicate agglomerates intercalated between clay sheets was found. And the nanosilica reinforced pathway lead to a park morphology with regular distribution of silica phases in the clay matrix. And anyway, in all the synthesized composites, the amorphous silica phase was identified with a potential higher reactivity, and the specific surface area was also obtained, 228, 227, and 300 meters squared per gram, respectively, for CSS1, CSS2, and CSS3. And correspondingly, the microstructure evidence both an increased porosity and an increase in chemical active sites. We have the first work concerning the synthesis of the silica smectite clay-based composites have been published with all the other results, and we are going to now. I'm going now to present some elements, some results concerning the adsorption of beta carotene, which has also been published in some journals. Okay. These plots represent the effect of temperature and the contact time of the bleaching process. It can be noticed that for each type of absorbents, the bleaching capacity increase for each type of absorbents. Either the first one, CSS1, CSS2, and CSS3, and the enriched clay fraction without silica, CSS0, it can be noticed that the bleaching capacity increases with the contact time to reach an equilibrium state. It can then be found that the beta carotene elimination began with a speedy rate, obviously due to the high concentration of surface active sites at the initial time. This speedy phenomenon lasted longer at 60 degrees with the equilibrium time of 60 minutes and less than 75 and 90, unless for 75 and 95 degrees Celsius. And for 95 degrees Celsius, the equilibrium time was 40 minutes. So it is follow the steady state. We also noticed a steady state indicating the equilibrium. And for the last two temperatures, 75 and 95 degrees Celsius, the equilibrium time obtained is within the range reported in many works, generally between 15 and 45 minutes. This means that adsorption equilibrium time decrease when the temperature increase. And the reduction of time with temperature, with increasing temperature, was also observed by various authors. It can be understood that the increase in temperature results to less viscosity of the oils and rapid diffusion of the beta-carotene. So less viscosity, increasing temperature leads to less viscosity and more mobility of beta-carotene towards the surface of the adsorbents. Moreover, the rise in temperature is known to be a mean of adsorption site activation, which obviously led to a rapid adsorption of pigments. So for this first step, we maintained 45 degrees and 40 minutes as the optimal condition as per contact time and temperature. This plot shows the for each absorbent. For each absorbent, the bleaching capacity has a function of adsorbent dosage at 60, at 75, and at 95 degrees Celsius. And with the respective equilibrium time of 60, we take the equilibrium time of 60, 50, and 40 minutes. At each temperature, the increase of absorbent dosage from 1 to 3%, calculated from the mass of oil, did not show a great improvement of the bleaching capacity. This means that even if the number of active sites available for adsorption raised with the increased absorbent dosage, the steady tendency occurred due to the trend of the obstruction of some sites and the limitation of the adsorbate molecule with higher amount of adsorbent. So for economic reasons, it may be good to limit the absorbent dosage at 2%. Also saw the effect of the adsorbent microstructure on the bleaching process at 95 degrees and at 95 minutes and contact time of 40 minutes. The values of the bleaching capacity that we can see, the values of the bleaching capacity for 95 degree and 40 minutes and those adsorbent dosage of 2%, the bleaching capacity at equilibrium are 64, 65, 69 and 70, 79 and 92 for CSS1, CSS2, and CSS3 respectively. So CSS1, 75, CSS2, 90, 98, CSS3, 90, 92. All of them are greater than 60% for the smectite clay. For the smectite clay without silica. The role of the absorbent structural configuration can be pointed out to understand the variation of the bleaching capacity from one absorbent to another. The structural configuration is the main difference between the considered absorbent and also an important parameter that can determine the availability and the quality of active site of the adsorption. In this regard, it can be observed that CSS3 which is a typical nanostructural configuration composite, exhibited the highest value of bleaching capacity. Yes, followed by CSS2 which is a delimited clay structure. in which silica nanoparticles are dispersed. The decrease of the bleaching capacity continue with CSS1, which is a mixture of crystalline layer physics and amorphous silica microparticle. This suggests different type of interaction between the beta-carotene and the various absorbent particles. Furthermore, it has been established in previous work that interaction between organic molecules like beta-carotene and silica-based inorganic molecule and inorganic matrix has mostly involved the PD conjugated bonding, and sometimes also involves Lewis acid bonding, as well as Bronsted site and Lewis acid site. We can see here the physical appearance of the oils after treatment with the different composites. Okay, concerning kinetic experimental tasks were compared to pseudo first order, pseudo second order, and intraparticle diffusion models, and the non-linear regression plots are given here. For better understanding of the correlation between the experimental data and the different models, we perform the non-linear regression plots, as you can see on this graph, and some extent have been obtained, and you can see that the model may suggest an absorption mechanism. Regarding the modeling data, pseudo-second order model exhibit highest values of S square of the correlation coefficient, corresponding to the lowest ones for root mean square standard deviation. And this model may suggest an absorption mechanism with two steps. It starts with the speedy step corresponding to the external diffusion of beta-carotene from the oil to the surface of the absorbent due to the gradient of concentration between absorbent and absorbent surface. And the following step is a steady one that can be ascribed to the interaction between the absorbent and the absorbent particles. On the same line, we have compared the equilibrium experimental data to Langmuir and Furnish models, which are very used in the absorption of pigments like beta-carotene, and the non-linear regression plot were also performed. And we can see that for all the three absorbents, the Furnish model yielded a better fit than the Langmuir model, as shown by the coefficient, the correlation, the non-linear regression coefficient that we determine. We see that the highest value for Langmuir model is 0.0. The highest value of our Langmuir model is 0.7495, and the one of Furnish tends towards unity. This confirmed that the heterogeneity of the surface of an occurrence of a heterogeneous distribution of absorption sites on the absorbents. It is obviously in good accordance with diverse structures, with the diverse structure of the three absorbents. It is implies that the absorption constant increase with temperature for each of the two models. And this approves that the fact that higher temperature increases the kinetic energy of the absorbent particle, and thus the frequency of collision between the absorbent and beta carotene, and then enhance the adsorption process. In general, as the Freundlich constants value increases, the absorption capacity of the absorbent also increase. And the value of n, this is another Freundlich constant, is in the range of 0, 1 or 1 over n is in the range of is greater than 1. That means the value of n is the value of n is all less than 1, and specifically they are between 0.05 and 0.5, and that appears to be in agreement with the literature, with the usual range of 0.1, showing affinity between the pigments and the absorbent surface. Thermodynamic constants were obtained by varying temperature from 333 degree Kelvin to 368 degree Kelvin. The table you have here present the values of the Gibbs-free energy, enthalpy, and entropy from each composite. It can be noticed that the Gibbs-free energy values are all negative, and those of enthalpy and entropies are all positive. Regardless of the absorbent, the Gibbs-free energy for beta carotene absorption decrease with the increase of the decrease with increasing temperature, indicating the accelerating role of the temperature. The negative value is a proof of the thermodynamically feasibility and the spontaneity of the process. Enthalpies were found to have positive value for all cases. And showing that the absorption process was endothermic for all the three absorbents. And the positive value of the entropies obviously show the randomness in the system. However, even if the thermodynamic parameters confirm the same tendency for the three absorbent, a further interpretation considering the structure of each absorbent might reveal a difference in the energy variation involved in the adsorption of beta carotene. Please permit me to go straight. They suggest regarding all what we have just explained, we suggest the adsorption mechanism for the adsorption of beta carotene. It is a 2 or 3-step mechanism. The first step is the external diffusion of beta carotene molecule from the oil to absorbent surface, and the adsorption at the molecule surface. And the second step may be the internal diffusion of beta carotene to the inner active site of the adsorbent. And the third step is the adsorption molecule on the surface. And we think that the beta carotene molecules are absorbed on the surface of the beta carotene molecule are absorbed on the surface of the adsorbent has carbocations. We have compared the bleaching capacity of our absorbents with some commercial absorbent found in the literature, and some references have been given here. And we think that our absorbent are of important interest since that they have been synthesized using low-cost materials, and the absorbent and they can reach up to 95% absorption rates of beta carotene. For conclusion, all the three composites demonstrated potential as multifunctional materials with and the palm oil bleaching using the three composite yields the satisfactory result 64, 79, 92 for CSS1, CSS2, and CSS3 respectively, and depending on the distribution of the size and silica in the ferrosilicate matrix. The absorption mechanism involves external and internal diffusion steps. And overall, the study highlights the effectiveness and environmental benefits of utilizing silica smectite clay-based composite from palm oil bleaching. Thank you for your attention.
Thank you.